Thank you very much. Thank you very much, David, for the introduction and all the organizers for putting this together. It will have actually stability in it, so I just didn't put on the very main thing doesn't quite have stability, but it's going towards that. So it's always a pleasure to be both here in Vienna and also to be at a great conference like this, the chance to talk to many people. So I'm very happy about this, even so very jet lagged. So this talk will have so Kerr-de Sitter space is a cosmological space-time, so it's a general relativistic space-time. So it was gravity, and while Schrödinger is more known for quantum mechanics, but gravitation has been a key part of this institute, as defined by the waterfall it shows. It's purely gravitation we brought here from the Alps. And what I talk about is joint work with Peter Hintz and Oliver Petersen. I will indicate the various parts. Oh, and one more thing. I'm also very grateful to Jeremy Safta for the great talk yesterday, because this way I can really shorten my introduction. So I hope to actually get a bit farther than maybe initially thought. Now, there are lots of slides based on what's on top, but I'm trying to skip most of these analytic details unless there are questions. Happy to go back to that at some point. Just for the sake of having a different sign, I'm changing my signature relative to Jeremy's talk to 1-3, so time is plus, space is minus. The only difference this makes is that Jeremy had the lambda g on the other side. Now it's on this side. So, and lambda is positive this way in both cases. So this is a Ricci g plus lambda g equals 0 is Einstein's equation with the cosmological constant. And so here, cosmological constant is positive in this talk. And so Jeremy talked about the lambda equals 0 situation. Both a big picture and then results, especially stability results, works of his with Kleinman and Georgi and others, and also the Fermat, Sforziega, Rodnyansky, and Taylor. It is in the nonlinear setting and also various results in the linear setting. So I will not really discuss this in what follows. But I will ask similar questions about Kerr-de Sitter and Kerr-de Sitter spacetimes. And so this is, again, just the positive cosmological constant analog of what he talked about. And just as in his case, the question is, we have this Einstein vacuum equation. And the question is that can we solve this globally if we perturb initial conditions of this simple spacetime, such as de Sitter or Kerr-de Sitter, and describe the global solution asymptotically. And so the way of asking this question, as already came up in Jeremy's talk, corresponds to that after suitable modification. So this Einstein vacuum equation is not a wave equation, but after suitable modifications, namely gauge fixing, it becomes a tensorial wave equation. And so with a little bit of interpretation, this initial value problem makes sense for this. Okay, so, and just as Jeremy pointed out, the diffeomorphism invariance of the equation means that if you have a solution, then any pullback by diffeomorphism also solves it. And so even if you have of course, there are lots of smooth diffeomorphisms. So if you have an initial hypersurface where you have your data, you have lots of diffeomorphisms that actually fix that. So even the initial condition is not going to save that, or neighborhood of it, it's not going to save you from this. So there's an infinite dimensional non-uniqueness in this problem. And one might say that, well, all right, so what's the big deal? We are trying to solve the equation. But really, at the end of the day, if you think about linear algebra, existence for linearizations is via duality. And I mean, that's sort of the most general, robust way of thinking about this. And the adjoint carries, of course, the same, it has the same invariance or linearized version, the infinitesimal version of this invariance. And so just like the original linearized operator having a big kernel, so does the adjoint. And so there are issues with existence, let's put it this way. So the gauge issues sounds like, okay, there's non-uniqueness, but actually it really means also non-existence. And actually that relates to the formulation of the initial value problem. Really, your initial data is not quite initial data for a wave equation. It's on the initial hypersurface, you will have a metric and a two-tensor that you will want to be the second fundamental form or something that need to, of the solution, and they need to satisfy some equations, the constraint equations, which I'm just going to suppress from now on. So there's more behind. So I'm just going to concentrate on the equation, not on the initial value formulation. Okay, so how do you fix this? So Jeremy explained partially explained one way of gauge fixing. So maybe the one that goes back the longest is this harmonic wave or the third gauge in sort of various settings of Riemannian in particular settings. And so here what you do is you fix a background metric, which I'm denoting by G0. So this is on the same manifold. And what you require is that the identity map, so just pointwise fixes everything, from M to the metric you're trying to find to M with this background metric is a wave map. So wave maps have been talked about. So here, the identity map is the actual map, and you want it to be a wave map. So this is to satisfy, this is to say it satisfies a wave equation. So it's a one-form level wave equation essentially. And so so this is an extra condition you want. I mean, it sounds a bit funny, right? That you have an equation, you can't solve it, you impose an extra condition. It should be even harder. But the point is that you will get a better kind of equation, and hence you will be able to solve it. When you look at the Baire type of equation, you actually have to implement this somehow. And what that means is you have to, so this was the original equation, Ricci G plus lambda G is equal to 0. So the way you implement the gauge condition, so that this is the harmonic map or wave map condition. So you really want this some one form epsilon to be 0, and you will put it into the equation by taking its symmetric gradient. So this turns it into a symmetric two-tensor, and so now this equation at least makes sense. And so this epsilon is, I wrote it down in this slightly complicated looking way. So again, G0 is a fixed background metric. This del G is the divergence or negative divergence, so really the adjoint of the symmetric gradient. And this GG is what well, this is the general dimensional form, but in 4 dimensions, this is often called trace reversal. So this epsilon is a one form. So you think about to each G, associate this one form epsilon G. And then you will take its symmetric gradient, and this is what you plug into the equation. So it should be epsilon G comma G0, just like here. Okay. So now you have a new equation. And so the claim is that this is a nice equation. So in particular, it's a nonlinear, so quasi-linear tensorial wave equation, for which, for example, one has a nice local existence theory and things like that. So that's good. But of course, this is a method one can always use, that you start with an equation, you can't solve it, you change it, you solve that, but okay, did this do anything for the original equation? And so to relay this, what you use is the second Bianchi identity. So suppose you could solve this equation, then apply to this divergence composed with this GG. And so the second Bianchi identity is that the Einstein tensor, which is this Ricci composed with GG, that this is divergence free. And so similarly, this lambda G will go away. So the first two terms go away. And so what you do, so if you could solve this, you get del G GG of this big phi, which is del G GG del G star of this epsilon is equal to 0. Now, why is this good? This is good because, what is this del G GG del G star? This is actually a one-form wave operator, so I'm calling it here CP for constraint propagation. And so if it's a wave operator, so if you have vanishing initial data for this, And so this is the thing that you actually have to do when you solve Einstein equations, want to solve Einstein's equation given initial data. The initial data are not quite initial data for the wave equation. You have to sort of jazz them up to get initial data for the wave equation. And they should be such that the Cauchy data for this epsilon will be 0. This is the wave equation. Cauchy data are 0. The solution is 0. Okay, so the upshot is that once you arrange this, then this epsilon is 0. If epsilon is 0, phi is 0, and you solve the actual equation you want to solve. Okay, so this is just actually how this gauge condition helps you. So you get a tensorial wave equation which relates to the original non-wave equation because of a one-form wave operator statement. This sounds good. And so in particular, Choquet-Bruat. So I didn't say that if you take the background metric G0 to be the Minkowski metric, then this wave condition or harmonic gauge condition is at the coordinates of wave equations, and so this is what Choquet-Bruat used to show the local closeness. So this is like a geometric generalization of that. It's geometric, so now it makes sense globally. It's not just a local thing, but that doesn't mean that there are no global issues with it. I mean, number one thing, of course, when you write down something, is that it's very easy to write things down that don't make sense. So okay, this solves that problem. So at least it makes sense. But that doesn't mean it works. So and it doesn't. So it doesn't quite work. So there will be things to do, and so that's going to be the constraint damping. So that's going to be the last part of the talk. Okay, so what I talk about is global results for Kerr-de Sitter space. Actually, maybe just stepping back one thing. So Jeremy said that the first stability result was from Minkowski. So that's certainly true in lambda equals 0. Actually, for positive lambda, Helmut-Friedrich, so that's the Sitter space. So the analog of Minkowski is the Sitter space. So the Sitter space is the basic cosmological space-time that physicists love. I mean, that's what the universe is supposed to be like. And so in the mid-80s, I forget the date, he actually showed the stability of this in an appropriate sense. So it goes back, so de Sitter stability goes back a bit. And so this Kerr-de Sitter, just like Kerr in Jeremy's talk, is sort of a black hole in an asymptotically flat space-time. This is going to be a black hole in a de Sitter space, so in a cosmological space-time. So maybe I should just say that de Sitter space, one way you can think about it is that you take one higher dimensional Minkowski space and you take the one-sheeted hyperboloid in it. You pull back the Minkowski metric, this is going to give you a Lorentzian metric, and that's the Sitter space. All right, so it's the analog of hyperbolic space but in Lorentzian signature. Okay, so Kerr-de Sitter space is just going to be a family of metrics depending on two parameters, m and a, and just like in Jeremy's talk, this is mass and angular momentum. I'm going to think about this for this wave equation or stability problems. To think about this on a half line, so we're just going to think about the future. So there's T star, that's like a modified quote time unquote parameter, variable. There's going to be a radial variable, and then there's going to be a sphere. What this black hole nature corresponds to is the presence of certain null hypersurfaces. So hypersurfaces, well, maybe the easiest way to say it is that the conormal to them is light-like or null. So these are horizons. And so these will happen at certain values of this variable r. So in fact, two values that it will happen at is when this little r is equal to RE or RC. And so what we are doing here is we are taking a little bit bigger region, going from RE minus delta to RC plus delta, just like in Jeremy's talk. The reason is that horizons are complicated, they move around when you solve equations, so you want to give yourself room. You don't really want to be sort of limited to your horizon. I mean, it would mean extra work if you are. All right, now concretely, there's going to be a quartic polynomial, which I'm calling mu. So this is the analog or generalization of what Jeremy called, I think, a capital delta. And so here, remember, lambda is the cosmological constant, so it's positive. If you take lambda equals 0, then this r squared plus a squared minus 2mr is the Kerr, so the lambda equals 0, quadratic in that case polynomial. So here it's quartic. And so it's being quartic, it will always have 4, well, counted with multiplicity, it will always have 4 complex roots. And so we will call this space-time subextremal if it has 4 distinct real roots. And then I'm calling these R minus, R capital C, RE, and R little c. And we're really going to care about these 2 bigger ones, and so a region slightly bigger than that. And so here E is event horizon, which is the same thing as what was in Jeremy's talk, the black hole event horizon. And RC is called the cosmological horizon, which is completely analogous in terms of both local geometry and local analysis to the event horizon. But it's really, I mean, it's sort of nice to emphasize this because, you know, like black holes maybe sound a little scary, and you know, event horizon sound a little scary, but it's really event horizon. So it's a statement about the causal structure of the space-time. It's not about, you know, singularities of any kind. The same story here. The cosmological horizon just says that the space-time, I mean, I think the way this is put it is expanding so fast that you lose contact with your friends. It's not that anything goes wrong. I mean, it goes wrong because you can't talk to your friends, but from a singularity perspective, nothing goes wrong. Okay, so in any case, so we have a family of metrics, which I will write down in a moment. This quantity will be key in it. We are demanding it to have 4 real roots, distinct real roots. And this is equivalent to a discriminant condition, which you can express in terms of 2-dimensionless quantities, which is lambda m squared and a over m. Okay, and then here's a picture in which the coloring at this point doesn't mean anything. It just is a recycled picture, so you know, it has some coloring for recycling purposes. And the subextremal region is really this sort of curvilinear quadrangle, quadrilateral. So this is the lambda m squared axis. This is the a over m axis. So you think, if you think of lambda is just fixed, it equals to 1 or 3 or something like that, then this is m equals 0. So this would be de Sitter in that setting. So there's and on the other end, this vertical line is the well, a over m equals 0. So think of it as being a equals 0. So this is the non-rotating space version that short-short de Sitter. And this whole thing is a degenerate limit, which you can, funnily enough, both think about it as depending on how you think of this lambda m squared. But if you think about it as a lambda fixed and m is going to 0, this corresponds to de Sitter. If you think about it as lambda goes to 0, then it and say m is fixed, then this corresponds to the Kerr family actually, and they both show up in a funny way in a particular setting that I might get to at the very end. In any case, for now, is the interior of this, well, maybe plus this line, is what matters. And so this is the full subextremal region. Okay, so as promised, here's the metric. And as Jeremy said, you're really not supposed to be thinking about it too much. It looks even more complicated than Kerr. The main upshot of being even more complicated is that if you're trying to do anything algebraic with it, it's going to be much harder, which is a good reason not to try to do things that are algebraic with it. So, and then what you do, and again, this is the Boyer-Lindquist form. So this is singular at the horizon. So even though I really want to have this metric in a region like this, so R going beyond the horizons, in this form, I'm dividing by this mu, whose 0, 2 of whose zeros are the 2 horizons I care about. And so this is a singular metric, which is, as Jeremy said, is really a coordinate singularity. And so really things, really once you think of things going the other way, you have a perfectly nice metric on this extended space-time. For whatever historic reason, people like this sub-region in which it has this singular form. Well, you can always change back to the singular form by modifying the correct variable t star by some phi r, big phi r, and similarly with the angular variables phi's. Or you can think about the other way, that's more historically, that you start with this and then realize that you can change t and phi by appropriate quantities, so that the metric now extends smoothly across the horizons. You actually make even things real analytic, and then it doesn't sound like there's any non-uniqueness about it. Anyway, so the main thing you have to do in this is that this big phi and big psi has to, their derivatives really, have to satisfy certain things really at the horizons. That's the key thing. So this little f is supposed to be a smooth function, and it's supposed to be plus minus 1 at the two horizons. Otherwise, it just does whatever it wants to do, except that it's good to make sure that dt star, so t star is this thing, and I'm modifying it by this. It's good to make sure that it's time-like, which says that the constant t star hypersurfaces are space-like. So notice that this uses the dual metric. It's a statement about this one form, and this does not mean that dt star is time-like. So it's not going to be time-like near the horizons, for instance. So, oops, didn't I have a, it's after that I have a picture. Yeah, so here's a picture. So this is the same picture as Jeremy drew in a sense, except that now there are two horizons. And again, this is a recycled picture. So this R minus is really the event horizon. R plus is the cosmological horizon. The vertical axis is the T star line. This is the horizontal axis is the R line. And so every point in this picture is a sphere. And the region in which you are working is really R between two places, like R minus what's called here little epsilon, and R plus plus little epsilon. And T star is going into the future. So this is where you're really working. So this is the actual region on which one shows stability. And so this is where really so this picture on the left, so really analysis is what drives the problem, right? It's analysis on manifolds, maybe non-compact the way I drew it, but I will eventually make it compact anyway. Analysis drives the problem, so this is the fundamental picture. On the other hand, we are caring about a certain operator, wave operator, for which things like causal relations make a difference. And so the Penrose diagram, which looks like this, is of some relevance, but you should think of this as the primary picture. And the Penrose diagram, which came up in Folker's talk in particular, so the sort of 45-degree lines are, so think of this short Kerr-de Sitter, these 45-degree lines are null, and so these two horizons, so again, this is really R equals RE, this is the event horizon, this is the cosmological horizon, completely similar, and exactly the same causal properties. Once you cross here along a causal path, so that's closer than 45 degrees to vertical, you can't get back along the causal path. And that's just what happens on both horizons, so nothing drastic. All right, oh, I didn't say what the theorem is. Skip that. So here's the theorem. So this is a theorem from, by now, several years ago, I guess I can say. Very informal version with Peter Hintz. So basically the statement is that if you have initial data on your initial hypersurface, which satisfy the constraint equation, and which are close in some high regularity norm to the data of Kerr-de Sitter space with some parameters, so mass and angular momentum, with small angular momentum. Then there's a global solution G of the Einstein vacuum equation in this region with these initial data. And moreover, there are final black hole parameters M and A, so Kerr-de Sitter parameters M and A close to the initial ones, so that the metric asymptotically, as T star goes to infinity, decays to this slightly modified Kerr-de Sitter at an exponential rate. So the exponential rate is really fixed at the very beginning. And everything is quantitatively controlled by the initial condition. So just like in Jeremy's talk, I should point out that even if you start with a short Kerr-de Sitter, so that would be the A equals 0, A0 equals 0. A perturbation of that could be a slowly rotating Kerr-de Sitter, which of course solves the Einstein vacuum equation. And so it will not decay to a short Kerr-de Sitter. So it's the family that's going to be stable, the Kerr-de Sitter family. And so of course, under small perturbations, the parameters will only change a little. So if you perturb short slightly, you will get a slowly rotating Kerr-de Sitter out. If you start the slowly rotating Kerr-de Sitter, you will get a slightly different slowly rotating Kerr-de Sitter out of this. Questions so far? All right. So far it looks very similar to Jeremy's talking away. The matrix sort of settles down to a final metric, and in terms of say LIGO, looking at gravitational radiation, what you're looking at is the tail of the signal. So this is the complicated thing where you have your binary black hole merger or something, and that's very complicated. So numerical GR realm. What we actually know about sort of non-numerically is like the very end of it. Okay, so that's the main result at least in the slowly rotating setting. And of course, the natural question is, can one do this in the full subextremal range? So I have some comments about like what goes into proving this, and then I will comment on what extends to the full subextremal range or some part of it, and what one can do and what is still to do. So okay, so overall, the way we approach, so Peter and I approach this problem, so we think about this as even though this equation is not elliptic, we really think about it just like you would think about an elliptic equation. So it's really not an evolution equation perspective. In particular, we really solve everything globally, just like you would for an elliptic, linear or nonlinear elliptic equation. So globally in the region we are working in. This requires finite Sobolev regularity coefficients and so analysis with that. So right, that's life. There's actually a simple Nash-Moser iteration to deal with the loss of derivatives that corresponds mostly to trapping, in that the other part, the non-ellipticity, would be avoidable, just being more precise. And so it's really the trapping that I will talk about a bit, and that Jeremy already mentioned is what's sort of the biggest cause of this. But it's like once you start using Nash-Moser, you learn to love it, and it makes your life so easy, and then you stop worrying about the loss of derivatives. All right, so there are alternatives. So Jeremy's student, Alan Fang, did a different version of this for the iteration, but I mean, Nash-Moser is a perfectly good iteration, and it's actually, I mean, it's not a contradiction argument, right, or anything like that. It's in particular, in principle, perfectly implementable thing, especially if you use a nice simple version. I mean, you can just run it on a computer. It's a real thing. Okay, so these are the two things, so this gives global solvability for quasi-linear wave equations like the gauge-fixed Einstein, provided that two things hold. So one of them is some dynamical assumptions, and this I will talk about first. So here, this is, in words, it's like the only trapping is normal hyperbolic trapping with an appropriate sub-principal symbol condition. Okay, so I'll talk about this. And then the other thing is again something that came up in Jeremy's talk. So the mode solutions, you want there not to be any exponentially growing mode solutions with a precise condition on the non-decaying ones. So what is mode solutions? These are quasi-normal modes or resonances. So they're non-trivial solutions, the linearized equation at your favorite metric of the form that have this, well, it looks oscillatory, but the sigma will have an imaginary part that is greater than or equal to 0, times a function of the, quote, spatial variables, unquote. And so you don't want so when the imaginary part of sigma is positive, if I have my signs right, this is growing, and you really don't want that. I mean, for a linear equation, you don't care. It's perfectly nice. What's wrong with that? but for nonlinear equation, it's a sparse disaster. So, all right, and as I already said, everything is done globally in omega, like this Nash-Moser iteration runs globally in omega, and the linear solutions are done globally in omega. And the nonlinear aspects can be reduced to, I mean, after we're using these iterations, they're reduced to a precise understanding of the linear problems. And this just requires, because of Newton or Nash-Moser, I mean, Newton would be all right, for example, if you just do, if you don't have a trapping like de Sitter. So this requires a finite regularity version of the usual theory, just slightly more care. And try to point out that the sharp version of this, like linear theory, propagation, etc., was done in Peter Hintz's thesis, and in a more local setting was done by Beals and Reed back in the 80s, so quite some time ago. But once you, again, as I said, once you start using Nash-Moser, you stop worrying and says, who cares about derivative counts? Okay, so so all these things are valid, present already for nonlinear scalar tensorial wave equations. So that's why does I just think about those, especially in what I'll sort of trying to indicate the ideas. And in fact, the nonlinear aspects really do very little for you. So the linear theory is already gives you an idea what's going into it. And again, the limited regularity of the coefficients is not a big deal either. So I will really just discuss the smooth coefficient version of the linear theory. Okay, so so first of all, I want to say something about this dynamical assumptions being satisfied. So what this corresponds to is the phase space behavior of light rays. So light rays are null by characteristics. So the integral curves. So this is in terms of classical mechanics. They're integral curves of the Hamilton vector field of the classical sort of energy function or Hamiltonian, which we're calling Lilipy, which in PDE terms, so we have a wave operator is its principal symbol, which is, again, wave operator. This is just a dual metric function, so quote squared length, unquote, of a covector using the Lorentzian metric on T star m. Now, so we want some sort of statement about how these behave. So, and you really want to make uniform statements about this. And the easiest way to make uniform statements is on compact spaces, because uniformity is automatic. So of course you don't need compactness to get uniform statements, but you cannot make a mistake if you are in a compact setting. Then you cannot get away without making uniform statements, which is nice. You have to be forced to do the right thing. Okay, so here the non-compactness comes in two ways. One is that my M, which I don't know whether I really call M my manifold, but anyway, it has this T star going to plus infinity, so there's a spatial lack of compactness. And of course, T star, it's a cotangent bundle, the fibers are non-compact. Now, the fiber non-compactness is totally irrelevant because my principal symbol is homogeneous. So I really should quotient out by dilations in the fibers of the cotangent bundle minus the zero section. Even better, I really should be thinking, what I'm doing is really working at infinite frequencies, the high frequency behavior, like derivatives in sort of Jeremy's talk. That's what I really care about. And so what I really should think about is that I compactify the fibers of my cotangent bundle and to balls, just like in Folker's talk. In this case, it was Minkowski space that he was compactifying. This is a vector space. It really was compactifying as a vector space. Totally irrelevant that you had a metric on it. Here, the cotangent bundle fibers are vector spaces. You compactify them the same way to balls. This is a ball bundle on the underlying space. And you look at this boundary, the boundary ball is a sphere, so it's a sphere bundle, so it's a cosphere bundle. Okay, and then the other thing that you want is of course, you want to compactify the base then. And so here in this case, you can just use the exponentiated T star variable as the compactification. And so now, let me just draw a picture. You will have a space that roughly looks like this. So I have some extra directions, but this is so it's the zero section. So this is the boundary at fiber infinity of this fiber compactified cotangent bundle. Actually, I'm going to add the B to it, which I think I explain in a moment. And then this is, so this, it's at the zero section, so this is, of course, the same as the underlying space. I compactified it, and so this here is then the boundary of M. And so this is the compactified bundle over the boundary. All right. And so, so what we're going to do is to take our new phase space, which is, I'm calling this B cotangent bundle. This is like what so if you would like algebraic geometry, this is what the algebraic geometry is, I think, called the log cotangent bundle. So what you're really doing is you are, if you want in very concrete terms, you originally had something like a dRs and d angular variables as well as a dt star as a pointwise basis of your cotangent bundle, and you are extending this, so you're really taking this dt star seriously. From this new variable tau, it's d tau over tau, you're taking this all the way to the boundary. So you are really writing down this bundle in a trivialized way if you want, except it's natural, so you don't have to do that, and algebraic geometers love it. And they are very serious people, so you take it seriously too. All right, so the point is that I now have a compact space, whether I wanted it or not. I wanted it, but it's a compact space. You have a homogeneous function well on its interior, but the zero set is not well defined now on this whole thing, which is what's relevant. And then a rescaling of this Hamilton vector field is also going to be homogeneous. And it gives me in particular a smooth vector field on the boundary, which is tangent to the boundary. And I give it a name on the next slide, so here it is. And then, so what happens now is the following. So on the horizon, so we say this is my R axis here. So this is my T star axis, or e to the minus T star. So that's tau. This is my R axis. This is some fiber variable. So at the horizons, which is R equals to this RE and RC, I will have, and at tau equals 0, so that's this particular fiber. Within that, I will have a, within that, I will have a, what I'm calling here the B conormal bundle, so just the span of dr, the differential of R. And so this will act as a saddle manifold for this for the flow of this vector field HP. So I have this vector field HP. You should think right here on top of this picture. It's not really the top because it's not an interval bundle, sphere bundle. But okay, so it's sitting here on top. I have a flow on this. I mean, this is not just a compact space, a vector field on a compact space. This is a basic thing in a dynamical system. It has some critical points or subcritical manifolds. And I will in particular have some that are saddle points here. And so what it would mean that this flow is non-trapping is that all of the bicharacteristics, or not bicharacteristics really, so these are the integral curves of HP within P equals 0, so the energy shell, reach in finite affine parameter or tan2, so finite affine parameter if it's something like a Cauchy hypersurface, or tan2 if it's something like a saddle point, either initial or final Cauchy hypersurfaces, so initial would be like T star equals 0, that's where I want to start, so somewhere here, or R is equal to R epsilon minus delta, or RC plus delta. Let me go back to this picture. So yeah, that's like this. So these are the final surfaces. So these are also space-like. Space-like. This is space-like. This is initial, and this is final. That's why this picture is the Penrose diagram is useful because it's easier to see what's space-like. Okay. So non-trapping would say that basically all of the curves you care, all the light rays you care about, but again, you should really be in phase space, like physicists would tell you that you should always be. All of the bicharacteristics, both in the forward and the backward direction, reach places that you like. So either Cauchy hypersurfaces for obvious reasons, or this horizon saddle manifold, and that's good because you know how to propagate things through it. So this is, by the way, what I think Jeremy also mentioned, this blue shift or red shift effect. That really corresponds to, I really put it in terms of what happens at fiber infinity, but you should pay attention also to the linearization in the normal direction. It's really just an infinitesimal statement there. It is not true And the reason why it's not, this non-trapping thing is not true, but it's almost true. And the extra thing what you need is that there's an extra submanifold called the trap set, which is also a saddle point, but in a slightly different nature. What happens, maybe I'm not going to go through this given the time, but what happens, and so this I proved with Oliver a few years ago, is that in fact in the full subextremal range, the Hamilton flow, for the Hamilton flow, the only trapping is this normal hyper-trapping at gamma. So all back characteristics in finite affine parameter reach or tend to, both in forward and backward direction, either initial or final Cauchy surfaces or this horizon saddle manifold or the trap set. So this is really the statement I had at the beginning that all the dynamical assumptions are satisfied. Now, exactly. Yeah. And so then the other part was this exponentially growing modes. Now this has two parts. One, what do they mean? And the other one is, do they exist? But again, first you have to know what they mean. So, so what really you are doing is you're choosing an asymptotic killing vector field, or actual killing vector field. And what the quasi-normal modes are distributional eigenfunctions or object tensors or whatever of this, as well as being elements of the kernel of your operator, so it's the wave operator. And so concretely what we do with Oliver is we take this vector field, so it's a modification of dt star by a term that's 0 when a equals to 0. And this R0 is supposed to be some point in this interval RER, so that can be arbitrarily chosen. So it's not quite the same as dt star, which is what Peter and I used in the stability result. But for A small, they are very close, and everything we did with Peter was perturbation stable, so we didn't have to be more careful. Once you go to the full subextremal range, you have to be more careful, and this does the job. And so then the result with Oliver is that if you are more careful with the choice of this T, then in fact you get a discrete set of quasi-normal frequencies, and the space of quasi-normal modes corresponding to each is fine dimensional, and moreover, for solutions to small epsilon positive and for corresponding forcing decay, solutions to the forced wave equations have an asymptotic expansion in quasi-normal modes. So what this says is that the only obstacle to exponential decay of solutions of wave equations is really the quasi-normal modes. I mean, so of course this has been in physics. People have had this belief for a long time, but so now this is in this full subextremal range, and it's basically proved by this Fredholm theory setup that I introduced earlier in the Kerr-de Sitter setting, where I showed that various things are satisfied in limited range of parameters, and what this works do is to extend in the full range. And I think I'm almost out of time, so I'm just going to skip the details. Oh, okay. Yeah, it will be okay. Just do a few minutes. I just want to do one more point. So this is about wave equations. Now, Einstein was not a wave equation; it was turned into a wave equation. And so because of this turning into process, of course, you had some freedom, right? So first of all, we had the gauge that we were choosing. And second, we implemented the gauge. You should think of it as two completely independent things, more or less independent things. The implementation was the symmetric gradient. Okay, so, and so unfortunately, if you take this harmonic wave deter gauge, the dynamic assumptions are fine, but there are growing modes for the gauge-fixed Einstein, even though it's only a fine dimensional space. But I mean, that doesn't really help you so much if you're actually trying to solve your nonlinear equation. And so the key to actually proving the nonlinear theorem with Peter, given this analytic background, is somehow to overcome this. And so what then you would hope is that these non-decaying, in particular growing modes, come from the diffeomorphism invariance of the problem. So gauge issues, and plus, of course, the variance of the Kerr-de Sitter parameters, but that's fine, you understand that. So they are nonlinear solutions, so there are no issues with that. That's simple. But this is actually not true. So it's not true if you use this harmonic wave deter gauge that there are no, that the growing modes are related to diffeomorphisms. And this is completely explicit for de Sitter. So it's not just that we can't prove it, it's explicit for de Sitter. In particular, see the work of Graham and Lee in the Riemannian setting, so it's a hyperbolic space setting. It's exactly the same. It's a formal computation, just decided in de Sitter. Okay, so what do you do? Well, we didn't do, I mean, by we, I mean humanity did not do LIGO by just doing experiments. You needed numerical computation for it because you're really looking for a needle in a haystack. And so a key thing was constraint damping, which was introduced by, well, there's actually a precursor, I think, to this Gundlach papers and Pretorius numerical implementations for this binary black hole mergers. And so what you do is you modify the symmetric gradient by a zeroth order term. By the way, the symmetric gradient up to zeroth order term doesn't depend on G, so the G is sort of misleading. Anyway, and so what you do is you do a modification like this. So here's the symmetric gradient, and then you add to this, you somehow come up with a time-like one form, C, and you basically write down the most general expression you could using this time-like one form, and that sort of invariantly makes sense, and that's your modified symmetric gradient. And so well, in small a, we used, with Peter, we used just dt star with a particular choice of t star. And the particular choice used the critical point of this mu over r squared function in this interval re over rc. And for the full subextremal range, one wants to use a different c, which I'm not going to write down, but in particular, this the corresponding t star function is chosen using critical point of this r squared plus a squared inverse times mu, but there's some additional modifications. And in particular, if a equals 0, it's the same thing. That's what happened there. But if a is small, it's not the same thing. But again, the choice with Peter was fine for small a because everything was perturbation stable. Once you want to the full range, it's not fine. And so the statement is that for if you take this gamma very large and this e close to 0, then in fact this constraint propagation operator has no non-decaying modes. And since I'm out of time, I'm not going to go into exactly how this is shown, but it's again a second Bianchi identity argument. Basically, what it will tell you that non-decaying modes then of the actual equation you care about, the linearized gauge-fixed Einstein, are actually geometric. They are also mode solutions of Ricci plus lambda G linearized. And so let me just state this formally as an in progress, hopefully this year, but this is basically written down, this part. So again, this constraint damping works for the full subextremal range, so no non-decaying modes there. And so correspondingly, mode stability in particular, modulo diffeomorphisms, holds for the gauge-fixed Einstein equation in the full subextremal range, provided it holds for Einstein. And so in particular, if the ungauged Einstein mode stability holds for it's really any subextremal Kerr-de Sitter, then the full nonlinear stability holds nearby. Of course, there's an assumption here. This is Whiting and Schlapentok-Rothman in the lambda equals 0 setting. It's very algebraic, and this transformation that Whiting discovered. We don't know how to do anything similar in the Kerr-de Sitter setting, so the only thing we can do is the perturbation stability picture, and so maybe I can just go back to finish to the parameter picture I had here. So this green plus this corner, it's really the neighborhood of the vertical axis, is the slowly rotating. So here you get the mode stability by perturbation from the spherical symmetric case. So it's Reggie Wheeler, Zerilli, others adapted here using Ishibashi and Sato's others works in an invariant setting. And then this horizontal axis, this is actually where Peter Hintz in the scalar setting showed mode stability, neighborhood of that. It reduces to, how does this work in this full thing? So this is I said that you can think of this as de Sitter as well as Kerr. In fact, you get both if you think about it right. And so this is really using the Kerr stability result of whiting. So these two, and I'm pretty sure that it will work for the actual Einstein rather than just the scalar equation the same way. So this should be okay in the neighborhood of this. This is okay. As for the rest, I don't know. Thank you for your attention.